Right now, at this exact moment, the most expensive scientific instruments ever built by human beings are staring at the oldest light in the universe. They have been staring for 30 years, and the longer they look, the worse the picture gets. Not worse in the sense of blurry, worse in the sense that the universe they keep measuring does not match the universe in the textbooks, the numbers disagree, the shapes disagree, the timeline disagrees, and the disagreements are not shrinking as our instruments get sharper. They are growing. There's a cold spot burned into the back wall of reality that should not exist. There are holes in the structure of space so empty they challenge the math that describes how matter clumps together. There is something pulling 1,000 galaxy clusters in the same direction at 2 million miles an hour toward a point beyond the edge of everything we can see. And in April of 2025, Scientific American stopped calling one of these problems attention and started calling it a crisis. Stay with me because what I am about to walk you through is the single most important set of unsolved problems in modern physics. And in roughly 6 weeks, a telescope launching from Kennedy Space Center is going to point directly at several of them. I am narrator name, and this is channel name. Subscribe now if you want more stories like this, because the next few years in cosmology are about to rewrite the textbooks and I am covering every piece of it. Let me start at the wall, because to understand what is breaking, you need to understand what was supposed to be settled. If you point a sensitive enough radio antenna at any patch of empty sky, anywhere on Earth, any time of day, you will pick up a faint signal. It arrives from every direction at once. It has almost the same temperature in every spot, about 2.7 degrees above absolute zero, which is the coldest temperature physically possible. That signal is the cosmic microwave background. And it is, in the most literal sense imaginable, the edge of everything you can see. That light has been traveling toward us for approximately 13.8 billion years. It was released when the universe was roughly 380,000 years old, the moment the first atoms had cooled enough to stop trapping photons and let light finally escape into open space. Before that moment, the universe was an opaque fog of charged particles denser than the inside of any star. After that moment, it became transparent. The flash from that transition has been racing outward ever since, and it is still arriving right now at every telescope and every square inch of sky on Earth. It is the oldest light you will ever detect. It is the back wall of the visible universe. Every galaxy, every star, every black hole, every atom in your body exists inside the bubble that wall surrounds. There is no seeing past it with light. The wall is the limit, and for decades the wall looked almost perfect. The temperature variations across the entire sky are roughly 1 part in 100,000. Microscopic ripples on a nearly flat ocean. The math of the early universe predicted those ripples almost exactly. They are the seeds that grew into every galaxy you can see today. The model worked, the wall made sense, then we looked closer. In 2004, a NASA satellite called WMAP finished mapping the microwave background in more detail than any instrument before it. And sitting in the data, in the southern sky near the constellation Eridanus, was a patch of the background that was colder than the surrounding wall by about 70 millionths of a degree. That sounds impossibly small. It is not small. On a wall where the temperature varies by 1 part in 100,000, a dip that deep and that wide is a statistical outlier with roughly a 1 in 50 chance of existing at all. Not impossible, just deeply uncomfortable for a model that describes the wall as the most uniform structure in the observable universe. And the scale of it is difficult to hold in your head. The cold spot stretches across approximately 1.8 billion light years of sky. If you could travel through it at the speed of light, no stops, no detours, it would take you nearly 2 billion years to reach the other side. That is longer than complex life has existed on Earth. It is not a glitch. It is a feature carved into the oldest surface in existence. The leading explanation for the cold spot may be more unsettling than the anomaly itself. The best current hypothesis is that it lines up with something called the Eridanus supervoid, a region of space roughly 1 billion light years across, containing far fewer galaxies than it should, an enormous pocket of near emptiness in the structure of the cosmos. When light from the microwave background passes through that void on its way to Earth, it loses a small amount of energy. That energy loss registers in our instruments as a colder temperature. That sounds tidy. Except the void at the size required to produce this effect is also a problem. A void that big and that empty is not predicted by the standard cosmological model within the age of the universe. The math that describes how matter clusters together over 13.8 billion years does not produce holes of that scale. So either the void is not there, or it is there, and our model of how the universe builds its structure is missing something fundamental. And there is a third possibility that a small group of physicists have discussed for years without being able to rule it out. The cold spot might be a bruise, A mark left when our universe collided with or brushed past another universe in the first moments after the Big Bang. The math allows it. The data does not prove it. The idea refuses to die because no other explanation has fully closed the case. Think about what that means for a moment. One of the open explanations for a feature on the oldest surface in the visible universe is that something from outside our universe left a mark on it. But here is the part where this stops being abstract and starts reaching back toward you, because the wall is not just an interesting relic. The cosmic microwave background is the foundation on which we built our entire model of the universe. Every calculation of the age of the cosmos, the rate of its expansion, the amount of dark matter, the amount of dark energy, the future fate of everything depends on the assumption that we understand that wall correctly. If the wall has features we cannot explain, then the model built from the wall has cracks in its foundation. And right now, those cracks are showing up in at least 5 separate places at once. While we are talking about holes in the universe, there is one closer to home that deserves its own moment. In the constellation Bootes, roughly 700 million light-years away, sits a region of space approximately 330 million light-years across. In a typical part of the universe, a volume that size would contain around 2,000 galaxies. The Bootes void contains roughly 60. It was discovered in 1981 by astronomer Robert Kirshner, and even after 4 decades, no one has fully explained how it formed or why it is that empty. If you could stand on some hypothetical planet drifting through the center of it and look up, you would not see the crowded sky of stars and galaxies we see from Earth. You would see almost nothing. If a normal patch of the universe is a city at night, every window lit, the Bootes void is the center of Wyoming at 3 in the morning with the nearest town 1,000 miles away. Now point your attention farther south, toward the constellation Centaurus. There is something behind the dust of our own galaxy that has been pulling on us since before we knew how to measure it. In the late 1970s, astronomers noticed that the Milky Way was not drifting through space the way it should. Our entire local group, the cluster of galaxies that includes the Milky Way and Andromeda and a few dozen smaller ones, was being dragged toward a single point in the sky at roughly 1.4 million miles per hour. They called it the Great Attractor. For decades, the dust of the Milky Way's disk blocked the view. When X-ray telescopes finally peered through in the 1990s, they found a massive concentration of galaxies centered on the Norma cluster about 200 million light-years away. Enough mass to explain part of the pull, but not all of it. Further out, the Shapley supercluster, roughly 650 million light-years away and 4 times more massive, accounted for more. A chain of gravitational tugs across hundreds of millions of light-years, each link real and catalogued. That should have been the whole story. It was not. In 2008, NASA astrophysicist Alexander Kashlinsky published a paper that opened a problem nobody has been able to close. He was studying roughly 700 galaxy clusters using a technique that measures how the hot gas inside those clusters shifts the microwave background light passing through them. The effect, called the kinematic Sunyaev-Zeldovich effect, is one of the few ways to measure how galaxy clusters are actually moving through space, not just expanding apart from each other, but drifting in a specific direction relative to the universe itself. What Kashlinsky found was that the clusters were not moving randomly. They were all drifting in roughly the same direction at about 2 million miles per hour toward a point in the sky between the constellations Centaurus and Vela. He called it dark flow. The Great Attractor and the Shapley supercluster are inside our observable universe. We can point a telescope at them and count the galaxies they contain. Dark flow, if it is real, points to something outside the visible universe, past the wall, past the edge of everything we can detect with light. Whatever is over there, according to Kashlinsky's data, is massive enough and dense enough to grab 1,000 galaxy clusters and tow them through space from beyond the boundary of observable reality. The European Space Agency's Planck satellite later examined the same background at higher resolution. The results, depending on who you ask, either confirmed dark flow at a smaller scale or ruled it out. Nobody has settled the argument. If you are the kind of person who stays for the real science instead of clicking away, drop a like right now because it genuinely helps this kind of content reach more people who want to hear it. Now zoom forward to Christmas Day 2021. The James Webb Space Telescope launches from French Guiana and parks itself 1 million miles from Earth at a gravitationally stable point called L2. It is the largest and most sensitive infrared telescope ever built. It was specifically designed to look backward in time to catch the faint stretched light of the very first galaxies that formed after the Big Bang, and what it saw when it started looking broke something. The standard model of cosmology predicted that the first galaxies should have been small, dim, and messy. Loose clouds of gas slowly assembling themselves. Big, well-organized galaxies were not supposed to exist until the universe was at least 1 billion years old. There simply was not enough time before that for gravity to pull enough material together. Webb found them anyway. In its first year of operation, the telescope began returning images of galaxies that existed when the universe was less than 500 million years old. Some appeared fully formed with mature stellar populations. Others were too massive, too bright, too structured for their age. One galaxy confirmed by spectroscopy, designated JADES-GS-Z14-0, existed just 290 million years after the Big Bang. It was brighter and more massive than anything that should have been possible at that point in the timeline. It was not one anomaly, it was a pattern. Across multiple deep field surveys, Webb kept finding objects that contradicted the expected timeline of cosmic assembly. In May of 2026, a NASA study led by Katrina Chworowski found that some of these apparently massive early galaxies were being brightened by hidden black holes at their centers, making them appear larger than they actually were. That explained part of the problem. But the same month, a separate analysis published from Rubin Observatory argued that other early galaxies might actually be even more massive than initial estimates, because a large fraction of their stars are too faint to detect directly. The problem is not going away. The early universe, according to Webb, was already grown up, and nobody has a clean explanation for how. Now the puzzle gets a bigger version, and this is the crack that has some physicists using the word crisis instead of tension. For roughly a century, every measurement of how fast the universe is expanding has fed into a single number called the Hubble constant. It is one of the most important numbers in all of physics. It determines the age of the universe, the scale of the universe, and ultimately how everything ends. There are two main ways to measure it. One is to study the cosmic microwave background, the wall, and calculate how the universe has expanded over its entire history. The other is to measure nearby exploding stars and pulsating stars, and calculate the expansion directly from objects we can see. These two methods should give the same answer. They do not. The microwave background analyzed by the Planck satellite says the universe is expanding at approximately 67.4 kilometers per second per megaparsec. The nearby stellar measurements, led by the SHOES team using Hubble and Webb data, consistently produce a number closer to 73. That is roughly a 9% gap, and it has held up across decades of increasingly precise instruments. In December of 2025, the Atacama Cosmology Telescope collaboration published results confirming that an entirely independent CMB measurement matched Planck's lower number, making the discrepancy, in the words of Columbia University cosmologist Colin Hill, even more robust. The same month, the TD Cosmo collaboration used gravitational lensing of distant quasars to measure the expansion rate through a completely different method and found results that deepened the puzzle rather than resolving it. Meanwhile, astronomer Wendy Friedman, using Webb data with a different class of stellar distance markers called the tip of the red giant branch, published a measurement of roughly 70.4, which overlaps with the CMB value within its error bars. Some researchers have pointed to this as a possible resolution. Others, particularly the SHOES team, maintain that Cepheid-based measurements remain at 73 with greater than 8 sigma confidence, effectively ruling out systematic error in their pipeline. The tension is not shrinking. In April of 2025, Scientific American ran a feature titled "The Hubble Tension is Becoming a Hubble Crisis," and in April of 2026, a community paper published in Astronomy and Astrophysics, Building a Consensus Local Distance Network, concluded that the discrepancy may signal a deeper issue rather than a simple measurement problem. If the two methods continue giving different answers, it means either there is a systematic error so embedded in our instruments that nobody in 30 years has been able to find it, or there is a piece of physics missing from our model, something happening between the early universe and now that changes how expansion works over time. That possibility just got stronger. The Dark Energy Spectroscopic Instrument, DESI, mounted on a 4-meter telescope at Kitt Peak in Arizona, has completed the most extensive three-dimensional map of the universe ever made. Over 47 million galaxies and quasars cataloged across 11 billion years of cosmic history. In March of 2025, the DESI collaboration published results from its first 3 years of data containing roughly 15 million objects, and the findings carried a single uncomfortable conclusion. Dark energy, the mysterious force driving the accelerating expansion of the universe, may not be constant. The Standard Model treats dark energy as a cosmological constant, a fixed property of space itself that never changes. DESI's data shows hints at 3.5 sigma significance that dark energy's influence may be weakening over time. If that result holds as more data comes in, it would mean the force controlling the fate of the universe is not a fixed number. It is evolving. The lambda CDM model, the framework physicists have relied on for 25 years, would need to be modified or replaced. Here is what I want you to take away from all of this. These are not separate curiosities scattered across an otherwise tidy universe. A cold spot on the oldest surface in existence that should not be that cold. voids in the structure of space that should not be that empty. A chain of gravitational pull pointing towards something beyond the edge of everything we can observe. A telescope showing us galaxies that grew up too fast. Two ways of measuring the size of everything that keep giving stubbornly different answers. And a three-dimensional map of 47 million galaxies hinting that the force driving the expansion of the universe is not the fixed constant we spent a quarter century treating it as. These problems are not isolated. They cluster around the same questions. How does matter assemble at the largest scales? How does the universe expand over time? And is the model we built to answer those questions starting to crack at the edges? The standard cosmological model, lambda CDM, is still the best framework we have. It explains an extraordinary amount of what we observe, but the edges are fraying, and the edges are where new physics has always lived. What comes next is not speculation. It is already scheduled. On August 30th of this year, 2026, NASA's Nancy Grace Roman Space Telescope launches from Kennedy Space Center aboard a Falcon Heavy rocket. It carries a mirror the same size as Hubble's, but with a field of view 200 times wider. It was built to survey hundreds of millions of galaxies and map the expansion history of the universe with a precision no instrument has ever achieved. It is pointed directly at the Hubble Tension, directly at the question of whether dark energy evolves, directly at the structure of cosmic assembly that Webb called into question. The Vera C. Rubin Observatory in Chile has already begun operations and will detect billions of objects, photographing the entire visible sky every few nights. The European Space Agency's Euclid mission is already flying, already returning data, already mapping the geometry of dark matter and dark energy across the full breadth of cosmic time. Within the next 5 years, we will either confirm the anomalies and rewrite the textbooks or explain them away with better measurements and close the most stubborn open questions in modern cosmology. Either outcome is enormous. One means we discover new physics. The other means we finally nail down the model we have been refining for a century. Either way, the edge of the universe is not going to stay quiet for long. Stand outside on a clear night somewhere far from city lights and look up. The sky you see is a thin layer of nearby stars in our own galaxy. Past them, invisible to the naked eye but real, are billions more galaxies. Past those, the cosmic web of filaments and voids stretching across billions of light years. Past that, the wall. Past the wall, possibly structures so massive that they reach through the boundary of the observable universe and pull on us from a place we may never be able to see. For most of human history, the night sky was a decoration. It took thousands of years to figure out that it was a place. Once we did, we started measuring. And what we found again and again is that the universe is bigger and stranger than the previous generation believed. We are now the previous generation. The instruments pointed at the wall right now are the ones that will hand the next picture of reality to whoever comes after us. And almost certainly that picture will not match the one in the textbooks today. If this kind of deep, research-grounded science storytelling is what you come here for, subscribe right now and turn on notifications. Roman launches in 6 weeks, Rubin is already scanning the sky. Euclid is already mapping dark energy. When those results start arriving, you are going to want to have already understood what you are watching. Drop a comment with which anomaly from this video surprised you most and share this with someone who needs to hear it because these are the biggest open questions in physics and they deserve a far bigger audience than they are getting. Thanks for watching and I will see you in the next one.